Welcome to the MOOCs course Advanced Thermodynamics. The title of this lecture is Introduction of Phase Equilibria. In this particular lecture, we will be discussing a few basics of phase equilibrium problems, and as well as we will be recapitulating a few fundamentals of classical thermodynamics. So, basically in thermodynamics course at UG level, what we study relations between states of a system that undergo certain kind of processes. That is, one can apply thermodynamic principles to both reversible and irreversible process to get the information about what is the power requirement or power obtained, what is the amount of heat absorbed or dissipated, what is the value of an unknown property of a final or initial state such as temperature, etc., pressure, etc., those kind of thing one can obtain by using the basic thermodynamics principles. That is what we study in general in basic UG level thermodynamics course. In this course, we use principles of thermodynamics to obtain composition of a mixture when it attains equilibrium between coexisting phases, especially when the phases obey non-ideality and mixtures are a kind of a multi-component mixtures, not simply binary mixtures, not simply ideal phases. When these phases obey the non-ideality and the mixtures are multi-component mixtures, under such conditions, if the phases are coexisting and there exists equilibrium amongst those coexisting phases, what is the equilibrium composition of a given species, those things we are going to calculate. We are going to study how to obtain those kind of equilibrium composition for a given system, where two or more than two phases are coexisting and there exists a equilibrium amongst those phases. So, then why we need to study such equilibrium problems being a chemical engineering students? Because in chemical engineering in general what we study species chemically react to form a desired product, and separation of product from other byproducts as well as unreacted reactants, etc. Those things basically generally we expect to occur in chemical engineering processes or any chemical plant. So, that means there is a kind of separation as well occurring, not only reaction, but there is a separation. Further, separation methods involve contact or formation of different phases, wherein through which one species of a mixture preferentially segregates, and also in industries have to follow pollution board regulations, so that to cleaning contaminated environments also requires separation methodology, right. Separation is occurring, that means definitely one species is going to transfer from one phase to the other phase. Those kind of transfer of species occur from one phase to the other phase. So, then at what rate are they occurring? Is it possible to calculate, or what is the equilibrium composition of those process or those species where the phases, two or more phases are coexisting? Are these things possible to calculate or not? Those things important to know, right. So, because of this importance of separation of species or transfer of species from one phase to the other phase is unavoidable in any chemical plant. Because of that reason, it is important to estimate the degree to which species transfer into a different phase as function of processing conditions of a specified temperature and pressure, those kind of things. So, because of this reason, being a chemical engineering student, it is important to know how to do phase equilibrium calculations. So, then what is phase equilibrium? Before defining the phase equilibrium, in general we see some kind of examples where we often come across this kind of transfer of species from one phase to the other phase. Let us say in our regular life experiences as well as in many other physiology, home life, industry and so on, there is a transfer of substance from one phase to the other phase. For instance, breathing. When we take oxygen from air and dissolve it in blood, while carbon dioxide leaves the blood and enters the air, there is a transfer of species, right. Similarly, coffee making, when we take these coffee grains into warm water, hot water, what happens? Water soluble ingredients are leached from the coffee grains into the water. So, there is a transfer of species from coffee grains to water phase, right. Similarly, stain removals, applying of cleaning fluid to dissolve and thereby removing the greasy spots, stains, etc. So, here also there is a kind of transfer of species from one phase to the other phase. These are a few general applications or generally we may come across in our regular life, and industries there are huge number of applications where the transfer of species takes from one phase to the other phase depending on the applications. So, it is not over exaggerating to say that in chemical plants there is a huge amount of phase equilibrium problem existing where the transfer of species takes place from one phase to the other phase. So, then there may also exist a kind of equilibrium, and when there is a equilibrium existing amongst those phases, what is the equilibrium composition, those calculations become very much important both from the design as well as the operational point of view as well. Okay. So, then this transfer of substances occur because when two phases are brought into contact, they tend to exchange their constituents until the composition of each phase attains a constant value. So, composition of the constituent that is being transferred from one phase to the other phase, that becomes constant in each phase. In each phase that becomes constant, but they are not equal to each other. Okay. So, we will see some examples as well. So, this state means the phases are in equilibrium. When their composition of each phase attains a constant value, that means there is no further tendency to transfer of those species or constituents from one phase to the other phase. That means the composition in each phase becomes constant, and that state means nothing but phases are in equilibrium. Equilibrium composition of two phases are often very different from one another, and this difference enables us to separate mixtures by distillation, extraction or any other phase contacting operations in general. Indeed, the difference between the equilibrium composition that defines how easy or how difficult of a given separation process. Let us say if you have a kind of methanol water system, and then what is the equilibrium curve of this system depends on that one. You can decide at a given temperature pressure whether the separation of methanol water mixture into methanol pure or almost methanol pure and an almost pure water separate phases. Is it possible or not? Those things one can understand. Okay. So, let us say if you have two phases, the composition of ith species one phase is yi, and then composition of the same species in another phase is xi. Then the equilibrium curve between these two phases, if it is like this, as given like this, okay. So, then we can say the separation is possible, because for at any xi, what we can see, the yi is different from xi value, and then difference is large enough, sufficiently large enough. That means we can say the separation is possible. So, this line is a kind of diagonal line, right. So, how much this difference between diagonal line and then equilibrium curve is there, that defines how easy or difficult the given separation process is going to happen, right. If the equilibrium curve is close to the diagonal line, that means we can say that the separation is going to occur very difficult. It is going to occur, but it is going to be very difficult, or the severity of the conditions may be required to get such kind of separations. Let us say if you have a equilibrium curve like this, further like this curve here in the second picture, we can see the equilibrium curve of that composition, whatever the ith component composition in in one phase yi, another phase is xi. The difference between these two values are very large, and then that very large, that we can understand how far it is from the diagonal line. So, we can see now here the difference between xi and yi is very much higher. So, compared to the first case, in the second case the separation is going to be much easier, because the yi and xi values are very much different from each other. Okay. So, let us say if you have a equilibrium curve like this here as shown in this third picture here. So, this is very much close to the diagonal line, very much close to the diagonal line. So, that means the separation is going to be very difficult for this. It is possible, but severity of conditions may be high, that separation cannot occur easily. So, we have to use a severe operating condition to get this separation to take place. Further, if you have a equilibrium composition curve like this given here, so here at certain point what happens, what you can see here. So, this is the equilibrium composition curve. So, at this particular point, the composition of that species I in one phase is equals to the other phase, because the point is lying on the diagonal point. So, that means under such conditions the separation is not possible. Separation is not possible. One has to make sure that this point moves away from the diagonal. Such a kind of changes in the operating conditions or changes in the feed mixture one has to do such a way that this point moves away from this diagonal point, so that the separation can take place. Okay. So, this difference whatever is there between the equilibrium composition, this enables us to separate mixtures by different types of phase contacting operations such as distillation, extraction, absorption, etc., those kind of things. Species composition at equilibrium depends on temperature, pressure, composition and chemical nature of the substance in the mixture, etc. Then what we need from phase equilibrium point of view, phase equilibrium seeks to establish the relation amongst various properties such as temperature, pressure, composition, that ultimately prevail when two or more phases reach a state of equilibrium wherein all tendency for further change has ceased. So, this relation, the relation between temperature, pressure, composition, that we have to obtain, that is what the essence of this phase equilibrium, and then those relations we have to solve to get the solution of equilibrium composition, etc. Okay. So, these equilibrium properties are required for the design of separation operations, which count almost 40 to 80% of investment of chemical plant. So, such high is their presence, right, out of the chemical plant in whatever the amount that is invested in designing and then installing a chemical plant, out of which 40 to 80% cost is dedicated or required for this kind of separation processes. Such important is the kind of separation processes in chemical plant. So, because of that reason it is required to establish these equilibrium properties, so that design of a separation operation can take place efficiently. So, in general, if you have a kind of chemical plant, what we have raw materials which may be having the required reactants. In addition to that, there may be several unrequired or undesired components should be there. So, there would be a kind of pre-treatment stage where separation takes place, and then because of that separation what we can do, we can take out the undesired components from the raw materials, and then desired ones we can take to the reaction stage, second stage, and then from here what we get the products and then byproducts we get in general. Okay. There may also be some unreacted reactants as well, right. So, then we go to the purification stage or separation stage, where unreacted reactants would be separated, and if required they can be sent back to the reaction stage, and then products would be further separated from the byproducts. So, this again separation is involved here. So, this chemical plant, the flow sheet of a common simple chemical plant indicates how much important are these separation processes. Since separation processes are very much essential in any of the given plant, it is very much required to find out equilibrium composition, if at all there exists equilibrium amongst those amongst different phases within the separation units. So, now let us consider a closed system. Okay. So, here we consider a closed system where there are two phases are there, alpha phase and then beta phase are there. The temperature is T and then pressure is P. So, this system is kind of a equilibrium, right. So, we have a kind of closed system. Within the closed system, this is a closed system. Within the closed system we have two phases, alpha phase and beta phase, and there exists a kind of a equilibrium between these two phases, and then once the equilibrium has been established, the equilibrium composition are given as x1 alpha, x2 alpha, x3 alpha and so on, so xn alpha. there are n number of components. These are in equilibrium with x1 beta, x2 beta, x3 beta, xn beta. So, there is a equilibrium, right. So, when we know if thermal equilibrium is established, the temperature has to be equal in either of the phase. So, that is the reason temperature we have only one, we are not writing T alpha or T beta separately, because this diagram depicting a system, a closed system where two phases are in equilibrium. So, when there is a equilibrium, temperature has to be same in both the phases. So, that is the reason only one T is shown here. Similarly, when there is a kind of mechanical equilibrium between these two phases, coexisting phases in this closed system, then pressure has to be same in either of the phases. So, that is the reason pressure also we have represented only one, we have not written P alpha, P beta separately. Okay. Now, there is a transfer of species, mass transfer is also occurring from one phase to the other phase. So, then what should be that composition, that we have to find out, but how to represent that equilibrium because of the mass transfer, because thermal equilibrium we know that T alpha is equals to T beta is equals to T. So, only one T we are writing, right. Similarly, mechanical equilibrium we know that P alpha is equals to P beta. So, that is only one P we are representing. Similarly, when there is a transfer of species, so then what is this? Is it a composition of that species, that indicates the potential, that is that indicating the potential for the transfer of species, that we have to find out. For that we are going to see now what it is. Is it a measurable like temperature, pressure? If it is not measurable, then what it is, then how to make a relation between measurable properties, etc. Those kind of things we are going to see now. Okay. Consider a closed system as shown in figure. It is strictly a closed system because only closed systems can be in thermodynamic equilibrium. It is not possible to have a kind of equilibrium in open system, because in open system mass flows into and out of the boundary, and for which driving force such as pressure gradient is required. If the mass has to flow into and out of the boundary of the system, that is in a kind of open system, then obviously there should be a kind of pressure gradient, then only mass will flow into or out of the boundary. Okay. So, then if there is a pressure gradient is required for this mass to flow in and out of the boundary as per the requirement, then obviously there will not be a kind of mechanical equilibrium. Obviously, if there is a pressure gradient, that means you are saying the pressure is not same everywhere. If the pressure is not same everywhere, or the pressure is not same in either for either of the either sides of the boundary, that means you are saying that pressure gradient is existing. Pressure gradient is existing, that means you cannot say that there is a kind of a mechanical equilibrium. Okay. So, that means, however, we cannot simultaneously have a pressure gradient and mechanical equilibrium, that is equal mechanical equilibrium in the sense equal pressure should be established either side of the boundary in an open system where the transfer of species or the mass flow is taking place in and out. Okay. So, that is not possible. If you want to have a mass flow in and out, there should be a kind of pressure gradient. If there is a pressure gradient, you cannot say that the system is in a mechanical equilibrium. So, if it is not in mechanical equilibrium, you cannot say that the system is in equilibrium, right. So, that is the reason the equilibrium problems are valid only for closed systems, or valid only for the closed systems. Thus, here in equilibrium analysis will be discussed only for closed systems. Now, in the figure, piston cylinder assembly is shown just to indicate that the system must also allow to change in volume to accommodate thermal and mechanical equilibrium if at all there is a change. So, it has to accommodate thermal and mechanical equilibrium. So, because of that reason, piston cylinder assembly has shown for a kind of understanding only. Just for a kind of understanding, this piston cylinder assembly is shown to indicate that system must be also to change in volume to accommodate thermal and mechanical equilibrium. For a system to be in mechanical equilibrium, we know that P alpha is equals to P beta. So, that is equals to one constant P. Similarly, for a system to be in thermal equilibrium, then T alpha is equals to T beta is equals to some constant temperature T. So, that is in both the phases temperature is same, in both the phases pressure is same if mechanical equilibrium is also there. For chemical equilibrium of species, So then what is this? Let us say ith species, this whatever the system that we have taken, it is having more than 2 components. Let us say one component we are taking I. Okay, for that component, what it is in the alpha phase should be equals to what it is in the beta phase. That we have to make sure. Is it if you think as a kind of mole fraction, then is it reliable or not? That is what we are going to do. Or in other words, driving force for species transfer is not apparent. Why it is not apparent? That we will see now. Measurable properties such as mole fraction or concentration does not represent the driving force for a species transfer between 2 phases. Why? Because for example, if you take air water system at equilibrium, then if you see this problem as a kind of transfer of oxygen from one phase to the other phase, then in the air the mole fraction of oxygen is 0.21. That means, if we think that mole fraction could be a choice to represent driving force of species transfer between 2 phases, then it would be absurd to imagine that oxygen will transfer from air into the water phase until its mole fraction becomes 0.21 in water. That is not possible. If that is the case, then in the water as well as in the air, the mole fraction of oxygen has to be equals to 0.21, but that is not true in any system that you take. Okay? Or otherwise, if you think that water would be transferring into air, then the vapor was almost all water, because water is almost pure, like pure water you have taken, air is having oxygen and nitrogen and other constituents are also there. If you think like water is transferring into the air phase as a kind of in the vapor form, then see water is evaporating and then getting into the air phase or vapor phase. So, it has to transfer until the entire vapor phase has to become full of water. That is also not possible. Okay. So, because of this reason, it is not possible to say that some measurable property like mole fraction or concentration of a system in 2 phases, that can be used to represent the equilibrium or the species chemical equilibrium between 2 phases. Okay. That is the reason we do not represent the chemical equilibrium in terms of mole fraction or concentration. So, then what it is? So, because obviously we know neither of these are possible for this case of air water. If you take any system, that is going to be valid, these arguments are going to be valid for any system that you are going to take. We have just discussed air water system, because we know in the air water system, like if you have the oxygen transfer in the air, you know that the oxygen mole fraction is 0.21. So, that system we have taken. Likewise, if you take any system, it is not possible to represent the chemical equilibrium of a system by mole fractions or concentration, or in terms of mole fraction or concentration, it is not possible to represent chemical equilibrium. Thus, unlike thermal and mechanical equilibrium, thermodynamic property that drives a system towards chemical equilibrium is not a measurable property, and that is chemical potential. So, that non-measurable property, for the time being, let us call it as a chemical potential. Okay. So, unlike in thermal and mechanical equilibrium, thermodynamic property that drives a system towards chemical equilibrium is not a measurable property, and that non-measurable property, for the time being, let us take it as a chemical potential, or let us name it as a chemical potential. So, chemical potential of ith component in alpha phase should be equals to chemical potential of same ith component in the beta phase, if there exists a kind of a chemical equilibrium between these 2 phases alpha and beta. So, we are going to see more details about this chemical potentials and all those in coming slides anyway. Thus, the aim is to calculate how species distribute among phases when more than one phase is present or coexisting. That is the point, right. So, you have to, the purpose ultimately, let us say thermal equilibrium or mechanical equilibrium, the pressure you are measuring or they can be measurable. So, that is straightforward, or maybe quite easy compared to the chemical equilibrium case. In the chemical equilibrium case, there is no such kind of a measurable thermodynamic property which represent the chemical equilibrium. We call it as a chemical potential, but what is that chemical potential? That is unmeasurable. So, then there should be a kind of relation between this unmeasurable chemical potential and other properties like temperature, pressure, composition, etc. So, those kind of thing we have to do. The aim is to calculate how species distribute among phases when more than one phase is present or coexist. These calculations are restricted to equilibrium systems only. Therefore, they give information on direction of the driving force for a given system, that is, the system will spontaneously move toward its equilibrium state, but that will not give the information rate at which it will reach equilibrium. Okay. Now, understanding the importance of phase equilibria, especially from chemical point of view, and then how to define a chemical equilibrium for a given system, it is also becomes important to describe the state of phase equilibrium, especially in terms of thermodynamics. Okay. So, how to describe state of phase equilibrium? So, aim is to relate quantitatively the variables that describe the state of equilibrium of two or more homogeneous phases that are free to interchange energy and matter. Then what do you mean by homogeneous system here? Homogeneous phases at equilibrium means any region in the space where intensive properties are same everywhere. If the intensive properties are same everywhere in the region, then we can say that is a kind of homogeneous, right. So, then what are the intensive properties? Intensive properties are those which are independent of mass, size and shape of the phase, for example, temperature, pressure, density, composition, etc. Okay. So, while discussing these phase equilibrium problems, wherever we have this basic thermodynamic terminologies, we are going to define them as well as a kind of recapitulation of what we have studied now in our undergraduate course. So, Gibbs phase rule is used to define number of intensive properties that must be specified to fix the state of equilibrium or the state of phase equilibrium unambiguously. If you fix the state of phase equilibrium, then it becomes easier or straightforward to obtain the phase equilibrium composition, etc. Okay. So, that is the reason it is if you wanted to describe the state of phase equilibrium, you have to use the phase rule, right. That is, in order to describe the state of phase equilibrium, you have to use Gibbs phase rule. What it says, in the absence of chemical reactions, number of intensive properties to be fixed should be equals to number of components minus number of phases plus 2, and this 2 stands for temperature and pressure. So, let us say for example, 2 component 2 phase system is there. So, then pi is 2. Okay. So, that means how many intensive properties are there? x1 alpha. So, x2 alpha is nothing but 1 minus x1 alpha, because it is a binary system we have taken. So, this is only intensive properties, x2 alpha cannot be counted as a separate intensive property. Okay. Similarly, x1 beta, 2 temperature, pressure, third and fourth. There are 4 intensive properties are there that are describing the system. Okay. These 4 intensive properties are there, out of which how many if you fix, then you can say that the state of phase equilibrium is described unambiguously. That you can know by the Gibbs phase rule. So, pi is equals to number of components is 2 components and number of phases 2 phases. So, 2 minus 2 and then plus 2 is there. So, that is pi is equals to 2. That means, out of these 4 intensive properties, right, that is x1 alpha, x1 beta, t and p, out of these 4 intensive properties, if you fix any 2, remaining 2 you can find out without any difficulty using these phase equilibrium problems, right. Let us say if you have a methanol water system, right, and then temperature and pressure are you are fixing it, assume this vapor and then liquid phases are at equilibrium. This methanol and water system that you are there. So, what you are trying to do, you are trying to separate them into almost pure methanol and then almost pure water kind of two separate phases, that you are trying to do, right. So, then and then obviously for this purpose what you are trying to do, you are applying certain pressure and temperature, right. Let us say pressure is 1 atmospheric pressure and then temperature let us say 60 degrees centigrade if you are fixing, for examples. Then by heating at this temperature and then this 1 atmospheric pressure, if you are keeping fixed in the closed system where you have taken this methanol water mixture, then obviously the phase separation will occur, that is vapor phase will take place because of the evaporation of the more volatile component. That more volatile component will get into the vapor phase and then less volatile component will be present in a kind of a liquid phase, right. So, then what is that equilibrium composition? Without doing experiment we can find out if that vapor phase that has formed is a kind of, let us assume, ideal phase. Similarly, that liquid phase is there, that after separation, that is also kind, let us assume, is a kind of ideal phase. Then we can use this YI P is equals to Xi Pi sat. This relation we can use, right. Pressure is anyway fixed. For a given temperature, Pi sat you can find out, and then from here Yi Xi you can directly find out. For two components, if you write, what will happen? For I have written on generalized one. So, that is, it is a two component Y1 X1 P1. So, Y2 P X2 P2 sat. So, now here in place of Y2 you can write 1 minus Y1, in place of X2 you can write 1 minus X1, right. Y1 X1 are the two unknowns, right. The P is known and then P1 sat P2 sat you can know from the this given temperature expression, right. So, Antoine equation you can use and then you can find out the saturation pressures etc. for at a given temperature for a given species. So, these are known. So, then from here these two equations are there, two unknowns x1 y1 are there. So, those things you can calculate without doing any experiments. That is the point of this phase equilibrium problem. Even if you have a kind of non-ideality in these phases, then we have this pi 1 and then gamma 1, this pi 2, gamma 2. So, these we can calculate, we can obtain this pi 1, pi 2, gamma 1, gamma 2 describing the non-ideality of vapor and then liquid phases, and then we can substitute here and then again y1 x1 we can find out. Okay. This is what mean by finding out or describing this state of phase equilibrium. Once you describe the state of equilibrium without any ambiguity like this, so we can use this phase equilibrium relations to get the phase equilibrium compositions without any difficulty, for example. So, not necessarily you need to fix temperature and pressure to get the x1 alpha, x1 beta for this case. You can fix x1 alpha and T, then you can find out x1 beta and P. Like that, any two intensive properties you can fix, so that remaining two you can obtain from the phase equilibrium relations. So, any two of these must be specified to define equilibrium and then the remaining two can be found. This is described only for a binary system and then two component binary mixture and then two phase system, right. So, but the same is true or holds good for any number of phases, any number of components that are present in the system. Okay. Now, definition and solution of phase equilibrium problems. So, we have seen the requirement, importance of the phase equilibrium problems in chemical plant. We have also seen the chemical potential, how to define a chemical equilibrium in terms of chemical potential, that we have seen. We have also seen describing the state of phase equilibrium. So, once you describe the state of phase equilibrium problem, then it becomes important to define and then find out the solution of phase equilibrium problems as well. Then only we can have a kind of a proper justification of studying these phase equilibrium problems. So, let us say we have a real life problem Okay. So, this real life problem, what we have to do? We have to convert in a kind of a mathematical form representing the real life physical problem. Okay. That we call it as a first step, where we are transforming the real life problem into a kind of mathematical form, mathematical equation. So, there should be a kind of functions to define this real life problem in terms of mathematical. So, what are those mathematical functions, etc., we have to find out. Then once you find out appropriate mathematical form or function of the real life problem, then we have to find out the solution of those mathematical problem. First, the real life problem we have to convert into a mathematical problem by using proper mathematical functions. Then those mathematical problems we have to find out their solutions, right. So, then when you have this solution, mathematical solution, so that mathematical solution would be in terms of some kind of mathematical or thermodynamic variables or properties. So, that is not a kind of real life measurable property. So, whatever the mathematical solution is there, that again has to be transformed into a kind of form of the solution which is having a real essence of a physical life, or real life physical meaning that solution should have. Such kind of transformation should we do, that we do in step 3, right. So, what do you mean by having a solution in terms of real life essence, or the having a meaning in real life essence? That is nothing but having the solution something like in terms of temperature, pressure, and then composition, etc. Because these are the things that you can measure. These are the things you can measure in a given phase equilibrium system in general. So, your solution should also be in terms of this one, then only you can find out whether the mathematically whether the mathematical solution is correct or not. Is it compatible, or is it validating with the experimental results or not? That you can find out only if it is having a kind of solution in the form of measurable properties such as temperature, pressure, and composition. That means, in the step 1, what we are trying to do, projection of the real problem into mathematical problem by the principles of thermodynamics. In other words, the importance of this step 1 is to define appropriate and useful mathematical function representing the real problem. So, what is that mathematical function? That is again very much important. Until and unless you know what is that mathematical function, you are not going to represent this physical real problem into the mathematical form. And then especially if there is a kind of chemical equilibrium, it is very difficult to have a kind of mathematical function in terms of measurable properties, something like mole fraction or concentration, etc. And then we have seen that mathematical function is nothing but the chemical potential if there exists chemical equilibrium amongst the phases. Okay. So, this has been disclosed by the Gibbs, that is Gibbs defined such a function as chemical potential. Now, surprisingly what you have to see here, the step 1, the mathematical function is chemical potential, right. And then we have to find out solution for this mathematical function, and then solution we have already found, it is already known through the phase equilibrium problem or the chemical potential. When we describe the chemical potential, we have seen the chemical potential of component I has to be same in all coexisting phases. So, that is the solution, mu I alpha is equals to mu I beta, like that. Okay. So, now surprisingly you can see that mu I itself is a kind of a function that defines the real problem into the mathematical form, rather transforms the real problem into the mathematical form. That function is nothing but the chemical potential, and again the solution for that mathematical form of the problem is again nothing but the chemical potential should be equal for a given component in all the phases. Okay. So, now solution is also mu I in terms of mu I, right. We do not know what is mu I, it is unmeasurable. So, then we have to convert it in terms of some kind of a measurable properties, or some kind of properties which are close to the real life situations, if not exactly in terms of measurable properties. We cannot write in terms of measurable properties because already we have decided, we have discussed, we have seen that this chemical potential is non-measurable property, non-measurable thermodynamic properties, unlike temperature and pressure. Temperature and pressure you can measure, but chemical potential you cannot measure. So, step 2 is about solution of the mathematical problem representing real phase equilibrium problem. So, mathematical solution of phase equilibrium problem can be represented by simple result at equilibrium, that is chemical potential of each component is same in every phase. That is, if there are p number of phases, mu I 1 is equals to mu I 2 is equals to mu I 3 is equals to mu I 4 is equals to and so on, so is equals to mu I p if there are p number of phases coexisting at equilibrium, or there are p number of phases and there is a equilibrium amongst all those p number of phases. So, this is the solution. Now, step 3 is about translation of mathematical solution into physically meaningful and acceptable form. Now, we got the solution, this is nothing but the solution of the phase equilibrium problem, but this is not having any physical meaning or acceptable form in terms of measurable properties, etc. So, this solution is as useless as nothing has been done unless if you have a kind of translation of this solution into a kind of physically meaningful and acceptable form, right. So, how to do that one? Let us consider equilibrium distribution of component I between two phases alpha and beta. Then mu I alpha, mu I beta you are having. So, that you must start with mu I alpha is equals to mu I beta, and this mu I alpha you have to make a relation. You have to make a relation or relate mu I alpha to temperature, pressure, x1 alpha, x2 alpha, x3 alpha and so on, so depending on the number of components present. Similarly, you have to relate mu I beta to temperature, pressure and x1 beta, x2 beta, x3 beta and so on, so depending on the number of components present in that phase, right. This relation you have to make first, then only you can have a kind of some kind of a physically meaningful and acceptable form of the solution. Now, to establish these relations, what we do, we introduce some auxiliary functions such as fugacity and activity, right. These fugacity and activity are much closer to physical sense than chemical potential. So, that means let us say if you take a vapor liquid phase or the equilibrium between a vapor and liquid phase which is having I number of components. So, let us assume alpha is a vapor phase, beta is a liquid phase, and let us take component I, there may be n number of components. So, for components ith component actually we can write it as yip phi is equals to xi fi naught gamma I, right. So, this is actually this is nothing but mu I alpha is equals to mu I beta. So, if you want you can have a kind of alpha here for pi I alpha, and then gamma I you can have a kind of beta like this for indication. So, now whatever the mu I alpha is there, that is related to the composition, its pressure, and then pi is anyway obviously function of temperature, pressure and then composition, that we are going to find out, right. And then similarly for the liquid phase, that is beta phase. So, we have it is now this mu I beta is related to its composition xi, okay, and then fi naught it's related, it's a kind of related to some reference state, fugacity at reference state. In general it is taken as PA sat, Fi naught can be taken in general as PA sat. So, the saturation pressure of that component at that temperature, okay, related to the temperature, that means, and then some auxiliary function gamma I beta, activity coefficient. So, this fugacity coefficient, this activity coefficient are a kind of auxiliary functions we are using to relate this chemical potential to temperature, pressure and then composition of the system. Further, these auxiliary functions fugacity and activity are coming from the concept of ideality, ideal behavior or ideal phase kind of thing. How it is, that we can see. Pi I is nothing but fugacity coefficient, and then gamma I is nothing but the activity coefficient. Fi naught is fugacity of component I at some fixed condition known as standard state. So, in general it is taken as a Pi sat for many other many cases as a reference standard reference. Okay. And this transformation comes from the concept of ideality. That means this whatever the fugacity coefficient, activity coefficient, they are not only some kind of auxiliary functions used to transform the chemical potential to, so that to relate them to the temperature, pressure and composition, but also they tell something about the ideality of the phases also. If it is a if the vapor phase is ideal phase, then fugacity coefficient is going to be 1. If the liquid phase is a kind of ideal liquid mixture, then activity coefficient is going to be 1 for that component. So, that means if this phi I, gamma I are deviating away from value of 1, that means there is a kind of a non-ideality in the vapor and then liquid phases respectively. Okay. So, what is the point? What is the importance of this activity coefficient and fugacity coefficient? First, they are a kind of auxiliary functions used to relate chemical potential to the temperature, pressure and then composition of the system, plus they are also a kind of indication about the degree of non-ideality that is present in vapor and liquid phases respectively. If they are equals to 1, that means vapor and liquid phases are ideal phases. For a mixture of ideal gases, phi I is equals to 1. Similarly, for a ideal liquid mixtures at low pressures, gamma is equals to 1 as I mentioned. If these are equals to 1, that means these phases are ideal phases. Fi naught is given by saturation pressure of pure liquid I at temperature of interest in general. This auxiliary function are numerical factors of the order of unity that establish the correlation between the real mixtures and those by ideal mixtures. Okay. Without this information of Pi and gamma I, we cannot have a kind of phase equilibrium problems, or we cannot solve the phase equilibrium problems where these phases are having non-ideality. If you have a phase equilibrium problems with non-ideality, then you must have some kind of provision to obtain these phi I and gamma I relations. Those things we are going to do in subsequent lectures anyway. In reality, for most cases we cannot assume ideal behavior and must establish following two relations. That is, Pi is equals to f phi function of Tp y1 y2 if and so if it is binary mixture. Similarly, gamma is equals to f gamma Tp x1 x2 and so on. So, it is not necessarily for the binary mixture, it is also valid for the multi-component mixtures as well. So, if you wanted to solve the phase equilibrium problems with a certain degree of non-ideality, before solving those problems, you have to establish these relations. What is this f of phi, what is f of gamma? These relations you have to establish. So, that is the primary part of this course for the first 5 to 6 weeks. So, we are going to establish these relations for many vapor and then liquid mixtures having non-ideality, and those non-ideality defined by different types of models. So, the references for this lecture are Engineering and Chemical Thermodynamics by Koretsky, Molecular Thermodynamics of Fluid Phase Equilibria by Prosnich et al., Chemical, Biochemical and Engineering Thermodynamics by Sandler, Introduction to Chemical Engineering Thermodynamics by Smith et al. Thank you.